Thank you, Morgan. I'm very excited to be here. Thank you all for coming today. And I'm excited to share some very surprising results of some work that we've done looking at what happens to red supergiants following failed supernovae. And so I'll kind of explain what those things are in turn. But first, just to get on the same page of what are red supergiants. Well, they're these evolved massive stars, so they've exhausted hydrogen in their cores where those squares are, and then they live up here in this upper right corner of the HR diagram. So they're very large, they're very cool, and so each of the black stars at the ends of these stellar tracks is where this model has its iron core collapse. And so what you see is the lower mass models don't do this, but then the stars above 10 solar masses, their iron cores collapse at the end of their lives. And in particular, these stars that are something like 10 to 30 or so solar masses, they die as red supergiants. So core collapse happens while they're in this red supergiant phase. And what's really important for what we're going to discuss today is the fact that these stars have these enormous, extended, fully convective hydrogen envelopes that are 500 to 1,000 times the radius of the sun. And also important is that red supergiants are the most common pre-supernova star. And so that means if we understand the transient signals that are associated with the deaths of these stars, then we can learn both about the massive stars before the explosions and the functions of the compact remnants that are left behind. So let's first talk about what happens in a successful sort of canonical explosion of red supergiants, and then I'll talk about what failed supernovae are. So if you have a successful supernova explosion of a red supergiant progenitor, then what we observe is a type 2p supernova. And so the type 2 just means that we see hydrogen in the spectra, and the P is for this characteristic, roughly 100-day plateau that we see in the light curves of these events. And a concept that's important for us at the end of this talk is just this idea that this plateau is happening because you have all of this hydrogen ejected. It starts out completely ionized, but as it expands and cools, you have the hydrogen recombined. So you're losing your electrons, which are your source of opacity. And so you end up with this recombination front that's actually setting your photosphere sweeping in mass coordinates through this expanding ejecta. And basically what happens is your photosphere ends up at the same temperature and approximately the same radius over this time, and that's why the luminosity is roughly constant, okay? And that just happens because you have this massive hydrogen envelope that's been ejected and is expanding and cooling. Okay, now, core collapse of these red supergiants doesn't always lead to a type 2p supernova or a successful supernova in general. Instead, sometimes the neutrino mechanism can fail. And so here I'm just showing you some example simulations of the sort of neutrino driving mechanism for supernovae. Both 1D simulations using a couple of different pre-stellar evolution models to model the red supergiants up to core collapse, and then some 3D simulations from Adam Burrows' group. And so each of these color points is as a function of the initial mass of the star. And the green bars and the green points are examples of successful supernovae. So these are the ones where if they're red supergiants are going to lead to the type 2Ps. Now on the other hand, all of the black points are examples of failed explosions where this neutrino mechanism doesn't revive the shock. And so everything basically stays bound. A black hole is unavoidably formed from the collapsing core and inner material. And critically, a large fraction of the hydrogen envelope is going to try to fall in and accrete onto this newborn black hole. And so the takeaway from these two plots is just that success or failure of the supernova is neither a monotonic nor a single valued function of the ZAMS mass of the star. And then the other thing, which isn't clear from these plots, but is clear from the literature, is that success or failure depends extremely sensitively on the pre-supernova structure of the star. And as we're learning today, the three-dimensional structure and evolution of the star just before core collapse. And so this is a very active area of research with details still being worked out. And so then the overall takeaway that we're going to carry forward with us is just this idea that an unknown fraction of red supergiant explosions fail. And so then the question is, well, what happens next? So for a long time, it was thought that if you have one of these failed supernovae and you have a red supergiant experiencing a failed supernova, then the star is going to sort of disappear quietly into the night because you don't have a rapid rotating core, so you don't really have a way of generating a transient. And so motivated by this idea that you could have a large fraction of red supergiants disappearing in these failed supernova events, Chris Kachanik and others have been studying about 1 million red supergiants in 27 nearby galaxies with just waiting for them to disappear. And so what they were looking for is just disappearing stars, or novae, some people call them. And so their best candidate so far for one of these events is this N6949BH1. And so what I'm showing you here is before and after images with Hubble Space Telescope of what they characterize as a 25 solar mass red supergiant. And so on the left here, inside this blue circle that they've helpfully added, you can clearly see the progenitor there. And again, that's a 25 solar mass red supergiant. And then in this later image, so that's in 2007, in 2015, this progenitor seems to not be there. Okay, so the light curve is interesting. So this is a light curve from about 2000 to 2016 of this star. And what you can see is before late 2008 or early 2008, this star in the optical, and I should say that the blue and the red and the green here are optical bands, and then the gray and the black here are Spitzer infrared bands, okay? And so this is just the luminosity as a function of time. And so prior to this brightening that happens in 2008, the star is just marching along at its sort of normal red supergiant luminosity. It undergoes this large brightening in the optical before dimming by more than 2 magnitudes in the optical below the pre-event luminosity of the star. And so what they theorize is that this red supergiant, in fact, had this brightening and then it totally disappeared. And so they say that this is a failed supernova event. Now, something that I want to point out, aside from this brightening, is you have this sort of persistent infrared source in these Spitzer bands. They say this is falling off as t to the minus 4/3. But what I'll explain in a second is the model that they think fits this brightening isn't necessarily consistent with this late time light curve. And so, clearly this red supergiant didn't have a 2p explosion. But if this was, in fact, the birth of a black hole from the collapse of a single star, we want to have a self-consistent theory to explain all the details of this light curve. And so that's sort of the central focus of my PhD research in the 2 projects that I'm going to talk about today. Okay, so, I said people used to think, oh, the star should just disappear, but you have this brightening, and so let's talk about what are the ways that you can actually generate a transient in a failed supernova. And so the first, which the Kachanik group says describes their data, is this mass ejection from neutrino cooling, which I'll explain. So all of these stars go through a protoneutron star phase before the protoneutron star collapses to a black hole. And so during this time, the protoneutron star is cooling by emitting copious neutrinos that carry about 1/10 to 1/3 of a solar mass of gravitational mass away from the core. And so the envelope, which came into hydrostatic equilibrium with the old core mass, suddenly feels the potential change. You launch a sound wave, which because of the falling off density profile of the envelope, accelerates into a shock, and so you can have this shock eject some material from the outside of the star. Okay, and now so this generates, so this generates a 10 to the 39 to 40 ergs per second transient for about a year, and something like for red supergiants, maybe a 10 to the 47 or a few times 10 to the 47 erg sort of explosion of this material from the surface of the star. Okay. And now I just wanted to mention this because people probably have this in their minds of, oh, this is what happens at a failed supernova. But what I'm going to show you today is that to some extent this is moot because the explosions that I'm going to show you that happen from infall of the hydrogen envelope actually completely overwhelm these energies and overwhelm the energy budget on the plateau. And so this really doesn't matter for the purpose of today. Okay, so I showed you my little spoiler. What's the other way that we like to generate an outflow or a transient? Yes, Kareem?
Just before you go to that, is 10 to the 39 or 10 to the 40 erg consistent with the amount that one event got brighter? Or is it?
No, it's brighter. Theirs is brighter, and that event is yet dimmer than what I'm going to show you. So I actually don't think that that's a field supernova. But I have a plot at the end that puts everything on a nice diagram so you can see. Okay, right. So the other way that we know and love to generate a transient is through accretion. And so basically what we have, let's just sort of back up, is that we've formed a black hole now in this failed supernova. And now we have this massive hydrogen envelope that's trying to accrete. And of course we know that if you have infall plus angular momentum, you can quite easily generate a luminous transient from accretion. And you know, famously in the case of rapidly rotating Wolf-Rayet stars, these can produce long gamma ray bursts. These are sort of the collapsars, and so we routinely see these. But the thing is, which I actually mentioned earlier, is that the cores of red supergiants are thought to be slowly rotating. And so when people think of collapse of red supergiants and failed supernovae, they don't typically think of being able to power a rotationally powered transient. And so, but what I will show you is you actually don't need rotation. And in fact, even in the absence of sort of net angular momentum, rapid rotation, the random velocity field in the hydrogen envelope alone, in this convective envelope, actually carries significant angular momentum and quite easily and naturally produces an explosion. Okay, this is weird, right? There's no net angular momentum, but then there's enough angular momentum to generate a transient. Let's step through that. Okay, so the hydrogen envelope, just think about this. You have this random velocity field in this spherical geometry, okay? And so basically, if you imagine, you know, a parcel of gas in that stellar envelope, it has this random velocity vector that's going to have some component of its velocity perpendicular to r, okay? So that means it has some specific angular momentum about the core, right? It has some motion, it has, right? Okay. It has some theta and phi velocity, so it has some j. Okay. Well, the thing is, though, is that you have a finite number of sort of convective eddies, I don't really like that terminology, in each shell, and so you're going to end up with uneven cancellation of all these little perpendicular velocity components in a given shell. And so that means that you're going to end up with some mean angular momentum in each shell, even if the total integrated angular momentum of the star is 0.
It won't be exactly 0. It could be up to square root of n, where n is the number of eddies, right?
Yes. It is related to the square root of n. And I can show the slide if there's time. But what I find is that sort of picture associated with the eddies and sort of like the local scale height and the square root of n, it works at large radii. But actually, what I'll show in my movies is that these convective motions cover many, many scale heights in the convective envelope, and they actually significantly enhance the specific angular momentum at small radii, even above the sort of initial theory that was thought of here. Kareem?
Is there a reason why it should have 0 net angular momentum anyway? Doesn't the star start out rotating?
Oh, yes. But I'm saying, let's say you have 0 rotation. Right? And yes, there are all these interesting things that will happen if you have a combination of this random field and rotation. But our initial question with this is, even if you have 0 contribution from rotation, does this matter? And if it's large, then what happens when the star collapses? And that's the rest of what I'm going to talk about today. Okay, so now I can't explain this paper, but I want to just take forward a result that Quadert, Laquenay, and Coughlin showed using some simulations of 1 scale height of the convective motion in a star, that this effect is really only important in the hydrogen envelope. And in the helium layer and farther down, the specific angular momentum is like 100 or 1,000 times smaller than what you need to orbit the black hole at the ISCO. And so basically, what we're going to assume going forward, and I confirmed this in my simulations, so I believe that this is true, is that this effect only matters for the hydrogen envelope. And so from the helium layer inward, all of that stuff is going to accrete spherically and be assimilated into the black hole. And so that's the assumption that I make in my simulations that I'm going to show you in a second.
Is the hydrogen envelope making it to the black hole, or could it be expelled?
It could be expelled if you had a jet from some other mechanism,
Exactly.
right? And so what I find, and so if you're familiar with this sort of jittering jet thing from Stoker's group, so they say that you would actually explode the star from like the oxygen layer or whatever inward, and so you would never get to the hydrogen envelope, but my results actually disagree with that. And what I find is that their estimate not only is too large by a factor of 100, but their estimate actually is numerically too small, but they say, oh, but you have magnetic fields in SASE, and so it'll work. That's basically, and that is something I'm doing the MHD version of these simulations that I'm going to talk about now. And so getting after some of these details of what happens when you actually do have this random velocity field and you have a tangled magnetic field and you're trying to accrete, what happens? And so part of that is because I think it's absolutely very possible that they're right, but we haven't shown it yet. So yeah, that's an interesting thing. Okay, so basically what we set out to do is say, okay, we know it's important in the hydrogen envelope, but these sort of like one scale height Cartesian box simulations that Daniel did for this paper, that's kind of not the geometry of the star. We also know, like from looking at Betelgeuse and other red supergiants, that these convective eddies probably span many, many scale heights of the star, and we're in the spherical geometry. So what we wanted to know is if we actually simulate that a little bit more realistically, what is the amount of angular momentum that's in this envelope? And then critically, once we have those simulations, we can collapse them to see what happens next. Okay, so let me start with the first simulations, and that is just simulating the hydrogen envelope. And so there's two things here. One is that this will now provide the initial conditions for the collapse, and I can also characterize the random angular momentum of the envelope before collapse. And so let me explain the model here, okay? And so this is a slice through the center of the star. This is a 2D slice, and so my simulation is a 3D star in a box. And so what I do, as I mentioned, is that we think that the helium layer and everything interior is going to be part of the black hole. So I assume all of that mass is just in a smoothed potential at the center of my domain. And then I stitch on this power law hydrogen envelope that then gives way smoothly to an isothermal atmosphere, okay? And so in large fractions of these red supergiant envelopes, the density structure really is a power law, and so we think this polytrope model is enough to study this question of the angular momentum content of this material. Okay, and now I want convection, and so I basically match the stellar luminosity coming out of the core with a heating source term. And then I have a cooling function out in this isothermal atmosphere that is my photosphere, which basically cools the gas as it comes up and rises so that I can get to convection. And so this is just the movie that I was showing in the beginning. And this is once I reach thermal equilibrium. And so what you see, which is consistent with our expectations, is that you have these large regions of cooled gas, of hot gas rising, and then they're intersected by these thin streams of material that was cooled at the photosphere. Okay, and so what we really want with these convection simulations is know that we're in thermal equilibrium. So this is just for the interested folks, that once I'm in thermal equilibrium, what I'm saying is that my heating rate and my cooling rate, so my time average heating rate and cooling rate, are equal, and those are both equal to the convective luminosity carried by the turbulent flow as a function of radius. So luminosity independent of radius, all of my heating rates match, thermal equilibrium. Oh, and I should say these are pure hydro simulations, and as I mentioned to Avi, and I can talk a little bit at the end, is we're doing the sort of MHD versions of these. So I just want to be clear there.
The radiation pressure is an important component?
No.
But isn't it?
No.
Gravity, it's not?
No, in these red supergiant envelopes, they're actually gas pressure dominated, and it's only after the shock passage that you have radiation dominated ejecta. Yeah. Okay, and so once I'm in thermal equilibrium, then what I do is, to make sure I've set my heating rate well, is then I look at convective Mach number profiles in my envelope. So these are just my simulation at different times over the region that I care about, and I'm comparing to a MESA model. And this MESA model is pretty typical of red supergiants. And so basically my setup, which is totally dimensionless, can be scaled to a variety of red supergiant models that have a MESA profile similar to this in their convective luminosity, or convective Mach number profiles. Okay, so good. So we have this convective envelope, this initial condition. Let's look at the angular momentum content. First, what I want to do, though, is because, yeah, this is weird, that we have a non-rotating star. And so we have angular momentum as a function of radius. So I have two plots here that I want to step through. And so what I'm showing you here is x, y, and z total angular momentum at different times. And what I've done is, this is cumulative angular momentum, so I've integrated out from the center of the star and out. And so what you can see is, at a given radius, so let's actually, let's take, I want one that, oh, this one, okay. So this is just at the latest time that I'm plotting. So basically, as I'm integrating over shells that are kind of on the inside, they all have sort of negative jy. But then as I integrate over more and more shells, I start integrating over positive jy, and eventually I get back to a zero total of that angular momentum component. So these are the components, but I actually prefer to look at the magnitude. And so basically, each of these is a component of a cumulative vector, and then I've just taken the magnitude here, okay? And so again, as I integrate over shells with angular momentum vectors that are oriented maybe one set of ways, I increase the total integrated angular momentum. But then necessarily I start integrating over shells with somewhat oppositely oriented angular momentum. And so once I'm outside the surface of the star, I'm back to zero. And so keep in mind that the black hole encounters this star as it's falling in, shell by shell as material is coming in. So the black hole has no idea that this star has zero total angular momentum. All it cares about is that each shell that's falling in has some specific j. Now this is in code units. What we really want to know is, how does this j compare to the specific angular momentum at the ISCO of the black hole? So I'm going to do that on the next slide. Okay, and so what I've done here, there's a lot here. So let me first step through this plot, and then we'll talk about the conclusions. Okay, so this is yes. Oh, yes, I'm sorry. That was just length units, code length units. Yeah, so that was a radial cumulative profile. So I'm integrating out in radius in 3 dimensions, and then I'm just plotting the cumulative value of those integrals versus r.
Right, so is R naught, so what is the...
R naught equals 1 in my code units. Oh, yes, I should, here, let me tell you this. Yeah, and Morgan will laugh because this was a ridiculous choice that I made, but like this was my first project as a grad student, like setting up simulations. But basically, R of 1 in my code units is here. And so basically at R of 1, the density is 1, the sound speed is 1, well, times like a gamma factor, and my characteristic velocity is 1. So like the free fall time is 1. And the photosphere of the star is at like 6 in my code units. Yeah, okay. But we're going to go to physical units next, so don't even worry about it. Sorry, yes?
Just another point of clarification. So once you have those angular momenta that you showed in shells, the idea is that they are frozen when the collapse takes place, right? That they don't have time to evolve. They stay whatever.
Well, it depends on the radius. So the outermost shells, the convective turnover time is shorter than the dynamical time, and so those would have time to restructure.
Okay.
But the innermost shells don't have time to restructure. But there's kind of 2 reasons that doesn't matter. One, I'm going to show you on the next slide, which is that it doesn't matter where or when you are in the envelope. You're kind of always j greater than j ISCO. The second thing is actually you're going to launch an explosion. This is like part 2 of the talk. You're going to launch an explosion way before you get to those shells at large radii. Yeah. So essentially, you can just assume it's frozen in. But the kind of neat thing is that, oh, that worked. Yay. Okay. Okay, so back to the space-time plot. Okay, so this is, radius is a function of time in the envelope, And so each column in this figure is the specific angular momentum profile of the star. So I've taken the mean angular momentum in each shell, and I'm plotting that as a function of radius at the time I took that snapshot. And I do that for every time that I have a snapshot for. Okay, but angular momentum, we're not normally used to thinking of the units, right? So what we kind of want to compare to is what is the radius, the circularization radius associated with that angular momentum? So at what radius will angular momentum become dynamically very important if you start with that specific J and you conserve angular momentum as you fall in? Conserve specific angular momentum, which is actually stricter. Okay, and then I'm dividing by the radius of the innermost stable circular orbit of the black hole. And so basically, all you need to keep in mind is that anywhere where this ratio is bigger than 1, that material is going to try to circularize outside the horizon of the black hole, and you have some hope of generating a transient or making a disk. But not only is it bigger than 1, oh, and I should say these white things, I've artificially applied like a base of 10 on this color bar to show you that everywhere in the envelope that ratio is bigger than 10. And in fact, typical values are hundreds to 1,000 times the ISCO of the black hole. So there is just no way at any time or at any radius or shell that you care about that this material is going to be able to spherically and quiescently accrete onto the newborn black hole. Okay, now I did a little bit of like a fast one because as I mentioned, when you plot the circularization radius, you're assuming the specific J doesn't change as you're falling in. And so before this project, we thought, well, we know that the initial thing is frozen in, but as stuff is falling in, everything has different like VRs. So is there so much mixing and maybe, other things? We knew there wouldn't be any really internal shocks. This is subsonic turbulence. And we were like, is this just going to like erase as this thing is falling in so it doesn't matter? And so the reason we went through all this trouble to set up this convective envelope was really hard running a star in a box on a thermal time. Actually, many, many thermal times. It was something like 500 dynamical times. The simulators are like doing this. Was so that we can actually answer this question of what happens once you have mixing and these other dynamical things happening as you fall in. Okay, so step 2 is these zoom-in simulations. And so let's put things in some real numbers. And this is dimensionless, and so I've just picked a particular star, an 18 solar mass red supergiant, to put these into physical units. And so don't like write home that it's always 0.1 solar radii. What we care about is the relative sizes. Okay, but just keep in mind that typically the angular momentum associated with this convection gives you a circularization radius of about 0.1 solar radii, okay? So that's what we want to resolve when we're falling in. And in my convection simulation, I just told you I'm simulating the envelope of like a 500 to 1,000 solar radius star. So in these units, my simulation domain, this is actually only a subset of it, is 2,800 solar radii in each Cartesian direction wide. My photosphere is at 840 solar radii, and so my smallest grid sail in the middle, where I've the most refined, is a solar radius. There's like no way I can resolve 0.1 solar radii in this simulation. Okay, so what I have to do is actually do zoom-in simulations where I actually take this data, I excise this region, and I put it into an entirely new grid, and then I add between 10 and 12 additional layers of static mesh refinement. And so what I'm able to get then is that my sync radius that I want to use to simulate the black hole is now a factor of 10 smaller than the initial circularization radius, and that my grid scale now is 10 to the minus 3 solar radii. So I've picked up a factor of 1,000 in radius by doing the zoom-in simulation, okay? And my outer boundaries don't matter because over the time that I care about, basically only like this innermost stuff accretes. So we don't even care about that. I just made the box arbitrarily bigger so we don't have to worry about boundary conditions. Okay, so what I'm going to do is jump to the sort of punchline of these simulations, and then I'll just step back and dial a little bit more in and explain why this is happening. So what I want to start with is, so we've simulated, we have this convective envelope. I introduce a sink at the origin to represent the black hole, which just allows material to fall in without feedback. And then what happens is we actually generate an outflow. And so I'm going to show you this in a movie. And so this is another slice through that 3D domain. This is actually a smaller region than what I showed you in the last slide. And there's two plots here because I'm just showing you two orthogonal planes. So you can get an idea of what is the shape of this outflow, you know, like is it totally spherical or not. Okay, and then what I'm plotting is the Bernoulli parameter in units of the local escape speed squared. And so if this ratio is very large, it means this material is sort of very unbound to infinity, okay? And now I'm only showing you material with positive Bernoulli parameter. All this stuff in the background, keep in mind, this is the stellar envelope falling in. It all has negative Bernoulli parameter because it's really bound. But it's a confusing movie if I show both of that material. So keep in mind that I'm going to show you this outflow going out. This is actually sweeping out through not just the envelope of the star, but the infalling envelope of the star. Okay, and so again, these are just two planes. And what you see is once I start having material where the circularization radius is larger than my sink, I start generating this outflow. And critically, once the outflow starts, my infall of some material to small radii doesn't stop. And so I'm able to continually, as material is falling in, keep feeding more mass and energy into this outflow as this envelope is collapsing. And so what you see is in here, this material has very large values of this ratio, something like a factor of 10. But then you see there are still these channels where material can reach large radii and sort of fall in. And also keep in mind that this material is starting out outside of here, and this is a shock front, a Mach few or more shock relative to the infalling gas. And so you're able to sort of thermalize this internal energy as this material is sweeping through. Okay, so now what I want to do is show you a movie where I've zoomed in at small radii so we can see what is happening there. Okay, and so again, this is just 2D slices through my 3D plane, but now I've zoomed in way at the origin. And what I'm plotting for you is the radial Mach number. And so blue stuff is stuff that is kind of going outward, red stuff is stuff that's coming in. And the way I've oriented these two planes is by taking the average angular momentum vector in this region of all this material. And so I've oriented the top plane so it's that angular momentum vector is pointing out. So like if we formed a disk during these times, we would be looking at a face-on view of the disk. The other plane is just the sort of orthogonal plane, and so this is the mean direction of the angular momentum vector of this material. And so if we did form a disk, this would be like the edge-on view, okay? And so in the paper, I included these other pink and blue arrows because it's helpful to, you can follow flows in three-dimensional space. Okay, so let's play the movie. And so essentially what is happening is material is trying to get to small radii, but it has too much angular momentum, and so it's circularizing outside the black hole. So it's being deflected significantly from spherical infall, radial infall. And then because of this sort of deflection, you have all of these interesting interactions happening between different parcels of gas. And so what's happening here is this material is trying to come in. You have some of these shocks here. You have all of this material running into each other. And eventually you're able to drive this material out. And this stuff is never able to come in. And so this looks parabolic because it's kind of that's what's happening, right? You have one parcel coming in. It has too much J. And so it follows this sort of elliptical or parabolic orbit, but then it's running into other gas and it's able to share its kinetic and thermal energy with this other material that now is being sort of launched out. And if you just look on the opposite plane, you can see this big blob is this sort of big cavity that's going out. And the important takeaway here is that we're having this continuous injection of mass and energy trying to get to larger radii and feeding this outflow. But critically, you always have these channels where a little bit of mass can fall in and probe deep into the gravitational potential and access these sort of large negative Bernoulli parameters there. Okay, and so the accretion rate is really important, and this is just sort of the mathematical expression of this movie, is that if I plot the accretion rate of material that actually makes it into my sink as a function of time, if you had spherical infall, no angular momentum, then your accretion rate would be here, about something like 50 solar masses per year, okay? But if I instead say, well, what happens if I take my initial snapshot and I say I only accrete material that should be able to fall in, right? Because I have a distribution of angular momentum. What if I accrete the low angular momentum tail, where its circularization radius is less than the sink radius? Well, then I would accrete at this rate. And indeed, I start out there. But as soon as I launch this outflow, I suppress the accretion rate by another factor of 10, and so, or actually more than that, and so I end up accreting at, 10 to the minus 1, where if I didn't have this angular momentum, I would be accreting at something like 50, okay? And so this is actually kind of remarkable. The convective Mach numbers in this envelope are like 0.1. So you have a 10% perturbation from hydrostatic equilibrium. This is like really small, but the envelope is so big, you have this huge moment arm, and so you have this huge source of angular momentum. And the thing to keep in mind is that previously people thought you'd have spherical infall. And if you have spherical infall, you can't generate shocks. You can't change your infalling potential energy to these other forms of potential energy. And so this is just really cute, I think, is that you have this small perturbation to hydrostatic equilibrium, which is these low convective Mach numbers in the envelope. But because you've changed things from spherical symmetry and you can probe deep in this potential well, you're able to have this accretion shock going out and you're launching this outflow from this star. Okay, how much time do I have? I think it's 45. Okay. Okay, so the important takeaway is that, if you're in spherical land, right, you launch an outflow, you stop your inflow, right? Accretion in some ways is a self-regulating process. Like we see this in galaxies, right? You launch this, cooling flow, I'm going to get all these words wrong. You kind of shut off the AGN accretion, but then later the stuff starts falling back in, and so you start launching a jet again. So like in a way, even in 3D geometry, accretion can be self-regulating. But in this case, even though, yes, we suppress the accretion rate, we never extinguish it. And that's really critical because we're able to, over time, integrate and get to like a huge amount of energy that's released. Yes?
So your co-author, Elliot, he worked on CDAF like 20 years ago or something?
Yes.
This is exactly that.
Yeah, so is it the same? That's
Yeah.
what my question is. Of course, it was in a different context. That was like
Yeah.
the center of a galaxy. So, but is it like that?
I would say no. Kind of, okay. I would say no in the sense that I want to be really careful about applying regular accretion disk assumptions and theories to this problem.
Yeah.
Because even in the CDAF, and all of these accretion models, and in the vast majority of studies of black hole accretion, you have material coming in with a fixed rotation axis. And yeah, the magnitude of that angular momentum could be changing in time, but this is really critical. The direction of the angular momentum and the plane in which you're trying to circularize does not change. And that means you have time for all of these interesting things like this convective-driven outflow, the MRI, radiation-driven winds, right? Not only do you have time for those things to work, but you have a natural channel where that material can escape. And so it's really important, and this is why we're doing the MHD version of this, is that when you have a tangled magnetic field and you have this, I haven't shown you a plot of the distribution of angular momentum in each shell. It's a factor of 10 times the mean. So when you have this very turbulent flow and this turbulent magnetic field, very tangled, falling in, you cannot assume you're going to make a disk, and you can't assume that some of these processes that will launch an outflow will work. So that's the only...
So it doesn't fit the accretion rate, the CDAF model.
Oh, no. He had me make so many plots of like M dot versus R. There were no halves or thirds or nothing. Yeah. Nothing like that, yeah. I read a lot of Ramesh's papers, very confused. There's so many names for things.
So you should give it a new name.
Yes, I was at CCA, and Matthew, who's there, was really trying to make me come up with a catchy name. But, you know, then you come up with things like jittering jets, which I like the theory, but I don't like the word. Yeah.
I think it is the CDAF.
Okay, we can call them,
Randomized version.
we can call them CDAF supernovae. How about that? Okay.
Oh, that'd be good.
Okay. No promises, though. Let's see what happens when we have magnetic fields, because those are definitely undoubtedly important in this problem. Okay, so I'm showing you this outflow. I have 2 plots left, and these are the most important. Okay, so what we really want to know is this outflow such that I can unbind the envelope? And if so, how much energy is in that explosion? And what does it kind of look like? And so that's what we're going to do with these last 2 slides. Okay. So what I do is I take my whole box way outside the radius of the star, and I integrate the total energy, including the gravitational binding energy, okay? And so this is just a plot of that integral over time. And so let's just focus on the black line. This is my longest running model. And so I start out at very negative total energy because all of the material is bound. I launch the outflow, and so I'm feeding this energy into this outflow. And so eventually my total energy, it basically increases monotonically over time. And critically, once I cross 0, that is formally the envelope is completely unbound, this curve doesn't even care, and it just keeps going, increasing monotonically. And now I should say that because I did the zoom-in grid, I can only follow this outflow about 1/3 of the radius of the star because I no longer have the outer radius of the star on the grid. And so this is sort of a minimum energy that I can get to based on my simulations. And that's something like 8 times 10 to the 47 ergs. Okay. Now, I didn't have time to add a plot of the velocity, but basically the outer shock velocity is constant in time. Okay? So this whole time, the outer accretion shock is going at constant v, something like 200 kilometers per second, 300 kilometers per second. And so let's just take that constant velocity and extrapolate until the outflow reaches the radius of the star. Okay? Yes?
So is the mass of your sink increasing here as material falls on it?
Yes. And it's accreting negative energy, which is why it's a bit confusing. You can get to positive energy. Like your total energy is not conserved in the grid, if that makes sense. Yeah. But this is the energy of the ejecta, basically. That's what you can think of. Everything over 0 is the energy in the ejecta. Yes?
So is your heating term like a viscous heating in the inner part of the accretion? Like what's heating?
No. So we only have heating in the convection simulations, right, to set up the luminosity. But we're assuming perfect accretion with no feedback, which we know is wrong. But again, MHD simulations. In those, we'll try to get to smaller radii. Right.
Yeah. So what's
Yeah.
injecting energy, I guess, to go from negative to positive?
You're accreting negative potential energy, and so the material that's left can have positive energy. And so don't think of it as injecting energy. Think back to that movie that I showed you where you're zoomed in. You have stuff coming in with negative Bernoulli parameters very fast. That is interacting with other material, and so you have all of these shocks and interactions happening that are able to take one parcel's sort of negative bound inflowing energy and hand it to other parts of the gas into positive kinetic and thermal energy of the outflow, if that makes sense. Yeah. Another way I could have done this plot, like let's say I wasn't like losing mass in my sink, is if I had done a slice and only looked at the material with positive energy and done that integral, it would basically be the same net number at the end. So just think of this as this is the total energy thermal and kinetic energy I have in the ejecta from this explosion. Okay, so what I want to do now is, so we have constant velocity, so let's just extrapolate this curve until the shock reaches the outer radius of the star. Now I want to emphasize this is an arbitrary time that I've chosen to estimate the energy. We actually expect the accretion to continue for at least a full dynamical time of the star, if not more, because the outflow is in these sort of large channels. It could take a while before you actually expand the whole hydrogen envelope enough to shut off accretion. So this is still just a lower limit of the energy. But if I extrapolate this curve until this shock reaches the surface of the star, what I end up with is something like a 4 × 10⁴ erg explosion. You eject the entire hydrogen envelope, which in this case is about 10 solar masses. And you have shock velocities of about 200 kilometers per second.
That's not a lot. I mean, this is a month, right?
Yes. So this is a lower
so
limit.
Over a month, this is 1% of a typical supernova energy over a month.
Yes. So it's not going to look like a 2p.
Right.
Yeah. Okay, let's see what it looks like though. Okay. Right, okay. So this is not going to look like a 2p, but, okay. So, but in order to make that estimate, we have to make some assumptions about what's setting the light curve, right? Okay, and so think back to the very beginning of the talk when I talked about in these 2p explosions, now these are at much larger energies. You have a lot of energy and thermal energy because basically the supernova shock deposited thermal energy in the envelope. So the energy sort of normalization is very different, but the physical process of how the light curve is arising is very much the same. Is you have this shock break out of the surface, you're going to have a little shock breakout, again, different normalization. But then you have all of this hydrogen that starts out ionized and it's going to expand and cool. You have this recombination front and you're going to have a plateau in the light curve, just like in a 2p, but at very different energies and luminosities. Okay, and so I said that you start out gas pressure dominated, but even these shocks, once you send a Mach 2 shock through the envelope, your radiation pressure dominated. And so I can apply some of the typical scalings of 2p supernovae of these radiation pressure dominated shocks, so some of the stuff from Woosley and Denkason and Arnett, to try to estimate what is the luminosity on the plateau and what is the duration of the plateau. Okay, and in particular I chose to use the formalism of Dexter and Kaysen because I don't want just scalings, I actually want exact normalization of these curves. And so this is a very rough estimate and this is a very busy plot. So let me explain what you're looking at here. So I can take these Dexter and Kaysen formalism, and so what this tells me is what is the plateau luminosity and what is the length of a plateau as a function of the mass of the ejecta and the initial radius of the ejecta. So this is 10, 100, 1,000 solar radii, same thing here, but these are for 10 solar masses ejecta, this is for 1 solar mass of ejecta. And then each of these colors says what is the energy of the explosion. So what is the total energy of this ejecta material? And from that, you just need those 3 things, ejecta mass, initial radius, and explosion energy, and then you can estimate the normalization of the luminosity on the plateau and then the duration of the plateau, okay? And so I should say though that it's actually kind of hard to do this at the lower energies, and so the luminosities are very, very, very close. The plateau durations could be off by like a factor of like 1.2, 1.5, something like that. Okay, but, right. So don't worry too much about the curves. What I want to show you is these 2 pink points. So what I've done is I've taken my explosions from my dimensionless units and scaled them to values appropriate for 2 different MESA models. One is a 16 solar mass red supergiant. The other is 11 solar mass yellow supergiant. This has a much less massive envelope. And what you find is that for the typical energies that I'm getting from my mechanism, these events would have plateau luminosities of 2 or a few times 10 to the 40 and plateau durations of something like 200 to 500 days. And remember the 2Ps live over here, and so those are much brighter, right? But the other thing that you have in this area is here I'm just showing you 3 examples of luminous red novae, which we think come from stellar mergers, either onset of common envelope or ejection of the envelope. And so these are a few of the sort of higher luminosity cases of luminous red novae, and those are these points here. And so what you see is that in this luminosity and duration space, there's overlap between those events and ours. Not visible on this plot is there are other similarities, is that you have the same physics setting the temperature, so the color is going to be the same. The ejecta velocities in a lot of cases are very similar, where you have components that are hundreds of kilometers per second. Some components might be a little bit larger. But then you're also going to have this kind of blue sort of 10-day shock breakout followed by this cool red plateau. And these look very similar also to a lot of the luminous red novae sort of two-peak light curves that we see. Like Monsi's student at Caltech, Viraj, has just released a sample of these luminous red novae and the intermediate luminosity red transients, which are similar. And so all of these fall in very similar parameter space. Okay, and so that just leaves open the question that maybe some small fraction of these luminous red novae could actually be the birth of black holes from singular stellar progenitors in failed supernovae. Okay, and so I'll end where I began, which is with this black hole event, and this kind of answers your question, Kareem. Is that sort of Lovegrove mechanism that I mentioned, the luminosities are like 10 to the 39 ergs, 10 to the 38 maybe, 10 to the 40. So that's sort of here. And so this is that failed supernova event that I mentioned, and there's really big error bars on the duration because they had really poor time sampling. But that event was here sort of, below 10 to the 40 ergs per second in luminosity. And I think that if this was really a failed supernova of a 25 solar mass progenitor, this event should be much brighter. But we don't have spectra of the event, and so it's really hard to disentangle what that actually is. The other thing is the late time light curve is a question. And so one of the things that we're motivated by with these results is just the idea that there's a little overlap in the space. And so one of the projects that I'm doing now, which I'll go to, is to actually simulate these, the light curves for these events. I'll skip the summary because I think everyone's been following along pretty well. So there's two things that we're doing. One is redoing this whole thing but with magnetic fields, because we know magnetic fields are important. And then the other thing is doing 1D light curves with radiation hydrodynamic simulations where we include the recombination energy and the cool temperature opacities that are really needed for the light curves for all of these events. And so what I'm modeling is just kind of a variety of weak explosions of red supergiants that kind of fit within all of these models so we can start to maybe disentangle the sort of immediate light curve of all of these events that fall in similar parameter space. And so that's all I have.
Questions? We have time for a few.
Yes?
So if you happen to be along the jet, is there a jet? No?
There's not a jet.
No jet.
No. Okay, Yuri 11 says, that looks like a jet. I don't think so. It's pretty time variable.
Right.
Yeah.
So you have a better chance of being at some point in time. So usually jets
Well, it depends.
So it will be a transient.
Yes.
Could be in the radio or gamma rays, whatever, but it will be short duration because then the jet will shift to another direction. It's worth checking.
Yeah, no, that's true. But then the other thing kind of related to that is the fact that it's not really a spherical explosion, and we do have different components of velocities along different lines of sights, and they're all roughly in the hundreds of kilometers per second. But the energy of the explosion and the sort of non-sphericity increases if I increase the resolution of my simulations and decrease the size of my accreting sink. So basically, more physical simulations amplify this effect. But then also adding magnetic fields where now I have a source of viscosity, where maybe now I start to circularize even deeper in the potential, I could potentially, that was not on purpose, increase the energy of the explosion.
You get a fast radio burst. Who knows?
Yeah, possibly.
A slow radio burst.
Yeah. Yes?
Yeah, so can you go back to the previous slide? So that was for the light curve prediction, right? And then it's powered by recombination. So if you look at the spectrum, it should look like type 2b. But for the luminous red novae, those are mostly dominated by interaction spectral features of nano hydrogen lights. So there has to be some extra luminosity there.
Okay.
On top of recombination.
Yes.
So I was wondering if you can make any prediction on the spectral characteristic here, and then if that matches with these transients or not.
Yeah, I don't think that I can. The other thing, though, is that, if you have, so you're saying that, and I guess it depends when you look at the luminous red nova. is you're saying you have the initial sort of ejection interacting with the material that was already there, so then you're going to have evidence of CSM interaction. But aren't there also luminous red novae where, like, you see those two peaks where you really are kind of seeing a shock breakout and then an expansion of this hydrogen? And then, so wouldn't they be very similar?
Maybe at that peak, yeah.
Yeah. Yeah, I think
Okay,
we're
so that's
meeting
what
later,
you're
and
right.
I also have some questions for you. Yeah.
Okay.
Yeah.
Yeah.
But I guess you said the shock velocity is 200 kilometers per second. That's much lower than the 2p, right?
It is.
Oh, yes.
Yes.
Yeah.
So a 2p shouldn't go below a few thousand kilometers per second. So I guess the spectra will look different in that sense because the shock velocity is like an order of magnitude smaller.
Right. But don't you expect to see like these in that far?
Right, but with 200 kilometers per second, that's going to be, you could.
Oh, okay,
yeah,
I see what
yeah,
you're saying.
yes,
Okay, so it looks much narrower.
Yeah,
and
yeah,
it might
yeah.
look like CSM.
Yes, yes, yes.
Green?
Could you go back one slide?
Yes.
So I'm still trying to understand how where the extra energy comes from. So I mean, one thing that happens, right, is some of the material goes into the sink and you lose its gravitational binding energy. But in real life, the black hole gains mass then,
Yes.
right, and that
Yeah.
cancels that out. So I mean, and you said you're only plotting the energy of the ejecta.
No, this is the total energy, but because the black hole is a sink source term, this ends up being, in practice, a plot of sort of mostly just the energy of the positive
So
ejecta.
there's no GM over R from the black hole included in this.
Yeah. I've included the gravitational potential. And that's why we start out below zero. Oh, right. But you're wondering, well, why doesn't the mass of the black hole grow in time?
Yeah, or I mean, just like, yeah.
Well, just to remind you of this plot,
Just think about accretion to a black hole. You usually can get the energy out of that.
Well, but that's from radiation.
Not necessarily radiation. It could be mechanical also. The jets coming up. So you put matter into the black hole, you get more energy out.
I see, okay.
and also keep in mind that I'm only accreting 1/100th of the total energy budget that I have in a given shell. Right? If I had perfectly efficient accretion, you could accrete something like 10 to the minus 5 solar masses and unbind the entire star.
Right.
Energy is not perfectly efficient, so it's something different than that. But I'm only accreting a tiny amount of mass in the black hole. But because the interactions are happening really deep in the potential well of the black hole, I'm able to convert that potential energy of that tiny bit of mass into this thermal and kinetic energy of the outflow.
Okay.
Evan?
I have a question on this slide, so this is great.
Okay.
Just to make sure, the first part is just make sure I understand the scale of the things we're showing on the left are.
Oh, right, 'cause it's in code units, sorry.
These are like infall and outfall Mach numbers, right?
Yeah,
You're
these
saying
are
that
radial Mach
convective
numbers. Yeah.
Mach numbers are kind of an order of magnitude lower than this, right?
Yes.
These are kind of 0.1, okay.
Yeah. Yeah.
So they are kind of seeding this.
Yeah, and if I showed you this
structure.
movie all the way out, outside of this, you wouldn't even be able to see it on the color bar because the convective Mach numbers are so much smaller.
Mhm.
Yeah.
Great.
Sorry, and what was your question?
So yeah, then the question is, right now we're kind of seeing roughly a particular snapshot, right?
Yeah.
Where there's a net angular momentum and we're looking at the disk face on.
Yeah.
If we could simulate long enough, would we see this disk kind of wobble around and
Oh, we absolutely do simulate long enough. So
Okay.
this is an incredibly tiny duration. I mean, look at the time scale is changing in the like 4th digit,
Right.
and I'm simulating in the 10th digit.
Right.
And so
okay,
for this movie, I've just done sort of, over the times I'm showing in the movie, I've taken the average angular momentum vector so that I can orient them in this way so we could get intuition from out of it. But actually what I show in the paper is some slices at just a little bit later time, and you don't see any of the circularization because actually the circularization has already moved to a different plane. So this thing is changing a lot over time.
So the disk is responding kind of in real time as different shells bring their net
Exactly.
angular momentum
Yeah.
and reorient it.
Yeah, so exactly. And that goes back to what I was saying to Avi earlier, is that you can't really just, immediately apply all the intuition that you get from these sort of AGN disks and collapsar disks where that angular momentum vector isn't changing in time, you can't just you have to be very careful if you're going to start making conclusions based on that theory with this, because this is completely stochastic, and in each shell, you also have a wide distribution of angular momentum. And so the mean kind of dominates, but it's sort of complex flow that's very time dependent, yeah. Both in a given shell and in the mean over time, if that makes sense, of the stuff volume. Okay.
I think we need to stop there, but let's
Yes.
thank Andrea again. Oh, and I should say that Andrea's schedule is pretty full today, but has openings tomorrow. So that's in that Excel spreadsheet. Feel free to sign up if you aren't already. Yeah.
Thanks everyone for your really great questions.
I think she might be able to come with you now, and then
Okay, that would be great.
and then maybe you'll bring her back, or I can come.
I will
I can
bring
stop
her
by your office.
I will, okay, so we can go to my
The key is that I don't.